So the resistance looking into the source is 1 by GM. So the bias circuit can provide 50 ohm resistance. The gate side, you have an infinite impedance. So that is the reason why proper matching cannot be obtained. If you ground the gate side, source and drain have finite resistance where the impedance can be matched. For common gate, the noise figure value is given here. It is very, very less when compared to the common source. So when you take the different values, you can find that for it is about 2.2 dB for long channel and 4.8 dB for short devices. So 2.2 is very decent and 4.8 is very, very large. So you can use this only for long channel devices. So noise figure will be worst at high frequencies when you consider the gate noise. So as we have seen, when you consider noise, the current noise present in the MOSFET, so at high frequencies, the noise figure will be very, very poor. So the how can I reduce that? It is using a resistor component only. You have to add resistors to match the impedance. Unless you match the impedance and at least achieve power matching, you cannot control the noise matching. So transit time effects also are reason for that, because the charge carriers take a finite amount of time to reach the one end to another end. So we need to enhance this transit time effect for achieving a proper power match or noise match. So one method is using inductive source degeneration. So what happens at the input side, you are going to have an inductance, and in the inductance will produce a lagging effect. So which will slow down your transit time. So that is going to help in achieving some benefits for me. So that is going to be one method where I have control over the value of the impedance. So see here at the input side, you see I have an inductance here, and if you find the input impedance, it is going to be SL plus 1 by SGS plus I approximately get this, and you can see the input impedance is that just like an RLC network, and the resistance is proportional to the inductance value. So you can find what is the feedback. It is going to be beta is going to be omega t by j omega. And if you find the impedance, it is going to be dependent on the inductance of your impedance. Okay. So capacitive degeneration contributes negative resistance to the input impedance, whereas inductive will contribute to positive, because at higher the frequency, the inductive impedance will increase, and lower the frequency, the capacitive impedance will decrease. So that is going to either add or reduce the value of impedance. Whatever the value of the resistive term, it is important to ensure that the resistance will always bring a thermal noise, and the reactance does not add any noise. So instead of adding resistance, why can't we add LNC, so that at least we can reduce the noise to some extent, and we can also provide proper impedance matching. Fortunately, there are numerous instances where narrow band operation is only possible. But if you are going to add inductors and capacitors, you can ensure that a wide band behavior is going to be possible by using these reactive components. Okay, that is the circuit is shown here. I am going to add one inductor LG at the gate side, and I am going to add one inductor LS at the source side. So how much LG and LS I'm going to add will decide how much amount of noise and power match I'm going to need in my